Welcome back, and in this video we are going to discuss Fermat's little theorem, or Fermat's little theorem. And so, just as a motivator, I want you to think about this finite field as F5, 0 through 4, okay? And the question here is, if we look at any element that is not 0 in F5, what is that element to any exponent? And you could talk about the exponent being in the integers or natural numbers, whichever you prefer. Okay, so pause the video, take a shot, write this out, and see what you get. Alright, well, hopefully you pause the video and work this out. 1 to the n is kind of boring, and I don't really want to spend too much time on it, but it's just going to be congruent to 1 mod 5. Okay, and remember, in a finite field, we do everything mod whatever the subscript is. Okay, but if we look at 2, 2 is a little bit more interesting. If you 2 to the first, that's going to be congruent to, well, 2, not 1. And then we have 2 to the second is congruent to 4. Okay, that's not too surprising. 2 to the third is congruent to 3. And then 2 to the fourth is congruent to 1. And then 2 to the fifth is congruent to 0. 2 to the fifth is 32. I'm sorry. 2 to the fifth is 2. I'm sorry. Try that again. Okay, and then the whole thing will repeat. Okay. 3, something similar happens. 3 to the first is going to be congruent to 3. 3 to the second is going to be congruent to 4. And then 3 to the third, which is 27, is going to be congruent to 2. And then 3 to the fourth, which is 81, is congruent to 1. And then 3 to the fifth is going to be congruent to 1, or to 3, I'm sorry. Try that again, 243. All right. Okay, so that's interesting. And then, again, it'll repeat. 4. Okay, if I look at 4, that's going to be congruent to, well, 4. 4 to the second is going to be congruent to 1. And, because 16, and then this ends up repeating. Okay, so something about repeating things pops up, and that we can actually see a little bit from Fermat's little theorem. And this is the statement, very useful in number theory. So if we talk about p being a prime and we have an integer, then we say that a to the p minus 1 is either congruent to 1 or 0, depending on whether or not p, this prime, divides a or not. Most of the time we're going to be dealing with things in this first case, and so we'll just be working with that. And then sometimes you might see the statement like this just rephrased, multiply by a on both sides, not a big deal. And so sometimes you see Fermat's little theorem stated as such. Okay, the proof is actually kind of fun, and there's a proof within the proof, so why not get 2 for the price of 1? Okay, well, there's kind of 2 cases we need to prove. One of them goes lightning fast, and I'm going to, just for time purposes, I'm going to kind of do this in shorthand, knowing that if I had more time, I would do it all out formally and include proper language. Okay, so the first case is if p divides a. Okay, well, if this happens, then certainly it's true that p divides any power of a. If we have a positive integer on there, and so then thus, and then this gives us that a to the k is congruent to 0 mod p. Okay, if we do this division, then there's not going to be any remainder. Okay, or if it perfectly divides, no remainder. Okay, so then let's look at that case where p does not divide a. All right, so then what we're going to get is a list of p minus 1 numbers. Okay, and for right now, we're just going to call them 1 times a, 2 times a, 3 times a, and etc. up to p minus 1 times a. Okay, that's just our list of p numbers. Okay, and we're also going to say that these are all reduced mod p. Okay, and I know that I can have this list with A in it because P does not divide A. Okay, so these are not divisible by P. Okay, so then now here's the proof within a proof. Here's the claim. The numbers in this list are unique. Unique or distinct, whatever synonym you want to use. And so we're going to go ahead and prove this. Okay, and so we're going to assume not. So proof by contradiction. Okay, so let's say there exists a JA that is congruent to KA mod P. Okay, well then rearranging, J minus K, A is congruent to 0 mod P. Okay, so then this implies that either P divides A or P divides J minus K. Okay, and this first one absolutely cannot happen. Okay, because otherwise, that's our underlying assumption of this whole section of the proof, so let's not deal with that. For the second case, what this means is that, well, if we're looking at J minus K, we know that these are both numbers between 1 and P minus 1, right? So let me just make that comment. So J and K are both between 0 and P minus 1. So then if I look at their difference, this is going to be at most P minus 2, or at least negative P minus 2. Okay, somewhere in there, right? And then if I think about if P has to divide this, what number P in this range divides J minus K? Well, the only number that divides, or that P divides rather, that P divides in here is 0. So that means J minus K is 0, and then therefore J is equal to K, mod P. Okay, so that's kind of the end of this proof, or this proof within a proof. Okay, so that's kind of our ending point there. But now, so we know that the numbers in this list are unique, and then next what I'm going to do, and this isn't necessarily something that you might think of on your own, I want to multiply the numbers in the list together. Okay, so multiply numbers in list. Okay, and if I do that, so that's A times 2A times 3A, dot dot dot, P minus 1A, what I end up getting is A to the P minus 1, and then P minus 1 factorial. Okay, but now remember that these were all numbers reduced mod P, so really these should be numbers, again, some permutation, but they should be, these should be, after we reduce mod P, 0, or not 0, 1, 2, 3, dot, 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 P minus 1. Okay, so if I multiply those together, this should all be congruent mod P to, well, and multiplying all those together just gives me P minus 1 factorial. Okay, and then I'm just going to write mod P. Okay, and then now you can cancel P minus 1 factorials on both sides, and we're left with A to the P minus 1 is congruent to 1 mod P. And that's the proof of Fermat's little theorem. There are many different proofs of Fermat's theorem. This is just the one that happens to use tools that we already know. If you are familiar with another version of proof, that is perfectly okay as well. Next, we will look at some applications of Fermat's little theorem.